Hello, welcome to Zigmatech Learning Hub. I will be your instructor for physics. For this class, we are going to be taking our exercises from Examguide app. If you don't have the application already installed on your device, I will want you to download the app in order to follow along in this class. Examguide is a leading educational app that helps students prepare adequately for various exams like UTME, post-UTME, WAEC, JCE, KCPE, IJMB, JUPEB, KCPE, BECE, JSCE, NCEE, NECO, etc. You can download the app from www.examguide.com or Google Play Store. Please subscribe to our channel and turn on the notification bell and get updated on new videos. Are you ready for this class? Okay, let's get started. Welcome to physics class, and today we want to talk about thermal expansion. The idea about thermal expansion is the fact that bodies when heated expand and when it's cooling contrast, and that is not the case for all the substances. Like we all learned about water. Water has the behavior called anomalous behavior of water, in the sense that water at a certain temperature will start behaving differently. However, in this class, we want to talk about the general understanding of what thermal expansion is all about. And the word thermal means heat. So we are talking about the expansion of a substance because of the application of heat. And this expansion has caused probably harm if not well utilized, and also it has been an advantage to areas that they are well utilized, like in the collapsing of building and in the railway. These and many more are what we'll be bringing to you in this class. So sit tight and let's get started. Now, by the end of this lesson, you should be able to explain the thermal expansion, even though I've given you a brief of it. Number 2, you define the linear expansivity and solve a few problems. And 3, you state and explain applications of thermal expansion. Now, like I said earlier, if you look at the clip on the slide, you realize that we are just using this simulation as a kind of heat. When this metal, which is called the stainless steel, is heated, you see what happens? It extends. That is exactly what happened. But in real life, these expansions are not very obvious. So when something is heated, like the zinc, even on the very hot day, metals expand. Just that the expansion is very small. Now, if you also see what you have on the screen, you realize that when we now have alumina, like fine ceramics, you see that the expansion is not as much as that of a metal steel. And that means that every metal has its own unique way of expansion, or its value of expansion. And that is what we call the constant of expansion or coefficient of expansion of different metals. Now, there are different kinds of thermal expansion. The first one, which is called the linear expansion. We also have area expansion, and we have the volume expansion. Sometimes they call this one the area expansion or superficial expansion, or sometimes we call this volume expansion, or sometimes we call it cubic expansion. But the one we call linear expansion is just an increment in length of a substance, especially metals, when heat is applied. And the same thing happens on the area. When you are talking about area, you remember we are talking about the length and the breadth of the body. And when we are talking about the volume, we are talking about all the areas, the length, the breadth, and the height. For example, what you are seeing on the screen now, you realize that this is the length. This was the initial temperature, T1. I am using T1 as the first temperature, and the T2 is the temperature when the body is heated, or when more heat is applied. Because even every substance has a quantity of heat on it. Just that application of heat is to add more to it. Now, if you have the first temperature, and we call this one L1, that means the first length. It could be 20, and when it is heated, it goes to a new length, which may be 25 or thereabout. So we'll call this one linear because of the length. Observation was only made on the length. We'll call it linear expansion. So when the observation is made, both the length, this one, D1 and D2, we now have a new bigger shape of the body. Maybe this is a rectangle, or yes, a rectangle or a square, provided that the increment was made both on the length and on the breadth. So we say that we have and area expansion, whereby the T2 is greater than T1. What I mean by this expression is that the temperature of this one, the bigger area, is far bigger than the temperature of the other one. So there is increment in temperature. So the same thing happens, and when you are looking at this, you are looking at a cuboid or a cube, and we are concentrating on the 3 dimensions, whereby both the A part, the B part, and the C part, they all increase. This is A prime, B prime, and C prime. So all the dimensions are increasing in their length compared to the original. So we say we have a volume expansion. Then, also, I want you to know that when you're talking about linear expansion, sometimes some books call it linear expansivity. We are saying that it's increase in length per unit length per degree rise in temperature, whereby we say that the linear expansion, we are giving this as the coefficient of linear expansion is given as change in length all over original length times change in temperature. So that is the formula for linear expansivity, with this as the coefficient of linear expansivity, which is the alpha. Sometimes, instead of writing change in length, we can say L2 minus L1. So, and whereby LO is the original length. This is the length before, this length is the length before the heat is applied. Then L2 is the length when the heat is already applied. Then this change in temperature, it could be, we could have change in temperature could be theta 2 minus theta 1. These are the parameters we use when we are talking about area expansivity. And this class will only concentrate on the area, and later on we talk about we are concentrating on the linear, and then later we talk about the area. Now the same thing we said there, this is the original length, which is LO. That is the original length before the heat was applied. Then now when the heat is applied, we now have LO plus this change in length. That means that little increment when the heat is applied. Now we have a very first question here. Now from this, we can talk about the linear expansivity, its SI unit. We can talk about the SI unit of linear expansivity, such that when we talk about change in length, we are talking about meter, right? When we are talking about, this is the line, when we are talking about original length, we are also talking about meter. And when we are talking about temperature, we are talking about Kelvin. So when this cancels this, we have 1 over Kelvin, or Kelvin per L, per 1. That is raised to power 1 over raised to power minus 1, which is the SI unit of alpha, is given as Kelvin per Kelvin, or Kelvin raised to power 1 over. That is why we always have this as K raised to power minus 1. So whenever you are solving a problem on linear expansivity, and then you have K raised to power minus 1, you know we are talking about the linear expansivity, because that is the SI unit. Now we are going to look at this problem. Steel bars, each of length 3 meters at 29 degrees Celsius, are to be used for constructing a rail line if the linear expansivity of the steel is 1.0 times 10 raised to power minus 5 per Kelvin. Calculate the safety gap that must be left between successive bars if the highest temperature expected is 41 degrees. So in this question, I'm going to still keep the relation here. I'm still going to keep the relation for linear expansivity as change in L all over L dot change in temperature. So in this case, we are going to look at the fact that L is going to be 3 meters. Then we have theta 1 is going to be 29 degrees Celsius. And we have the alpha to be 1.0 times 10 raised to power minus 5 per Kelvin. And then we have theta 2 to be 41 degrees Celsius. Now, in this case, the safety gap, that is, we are looking at the extension, and I want you to know that change in L is something as the extension. Yes, it's the extension. So in this case, I am going to apply these parameters because the safety gap is just the change in length. And I'm going to say that change in length is unknown. So we have 1.0 times 10 raised to the power minus 5 is equal to, change in length is what I'm looking for, all over. So the next thing is L, and the L is 3, I'll write 3, multiplied by, change in temperature means 41 minus 29, this is 3, and that is it, 13 degrees, that is 2. So in this case now, I'm going to make change in L the subject formula. I have change in L is equal to 3 multiplied by 12 is going to be 36 times 1 times 10 raised to the power minus 5. So change in length is going to be 3.6 times 10 raised to the power 1. I am writing this 36 as a standard form. Then multiply by 1 is 10 times 10 raised to the power minus 5. And the value is going to be 3.6 times 10 raised to the power minus, that is plus 1 minus 5 is going to be minus 4, and the answer is in meter. Or we can say that change in length is going to be 0.00036 meters. This is the safety gap that must be left in a railway in order to accommodate the expansion that must surely happen whenever the sun is heated on the road. We are going to look at another example of linear expansivity. It said the linear expansivity of a metal P is twice. A very technical question. Let's take it slow, one before the other. When we say that the linear expansivity of metal P is twice that of another metal Q, when these materials are heated through the same temperature change. All right? I'm going to say that this is for P, is given as linear expansivity of metal P. And then this for Q is going to be linear So these are the two metals and their linear expansivities. However, they say that the linear expansivity of the metal P is twice that of Q. Therefore, the linear expansivity of P is 2 times the linear expansivity of Q. This is very important. We need to keep this. Then they made another emphasis. They say that they are heated. It said when this material are heated through the same temperature change, that means change in theta for P must be the same thing as change in temperature for the body Q. That means if the change in temperature for a metal P is 50, then the change in temperature of the metal Q is also going to be 50, irrespective of the initial temperature and the final temperature. So having these two conditions picked from the question we are given, we are going to apply them in our formula and be able to solve the problem. Now, their increase in length is the same. That means their change in length is also going to be the same. That means change in length of P is going to be change in length of Q. This is another thing. It says calculate the ratio of original length of P to that of Q. All right. And let's see how it goes. Now, this is for P, is going to be change in length of P all over original length of P times change in temperature of P. That is it. Now, so this is what I'm going to write for this. I am also going to say that that the linear expansivity of the body Q is going to be equal to change in length of Q all over length of Q, change in temperature of Q. So these are the two formulas. Now, they say that one of these is equal to 2 of this. So instead of writing 1 of this, I'm going to write 2 linear expansivity of Q. Yes, this is what I have. Because 1 linear expansivity of the metal P is 2 times the linear expansivity of Q. So now that I have this, there is another thing. They say that change in length of the P is the same thing as change in length of the Q. So what I'm going to have is that now change in length of the length P is equal to 2 times change linear expansivity of Q multiplied by length of the P and change in temperature of P. This is what this one is. Yes, and also change in the length of the Q, of the metal Q, is equal to linear expansivity of Q times length of Q and change in temperature of Q. Now, since this and this are the same thing according to this relation, I'm going to say that, let me buy a little space for myself. I'm going to say that 2 linear expansivity of Q, L of P, change in temperature of P, is equal to linear expansivity of Q and L of Q, change in temperature of Q. Now, if you look at this very well, you realize that linear expansivity of Q, we cancel linear expansivity of Q. Then, remember also, look at this. Change in temperature of P must be the same thing as change in temperature of Q. Therefore, this and this are the same thing. So let me put it as P because they are the same thing according to the question. Then I'm going to cancel change in temperature of P with change in temperature of P. So we are left with 2LP is equal to 1LQ. I don't even need to write the 1 there, but you know it exists. So calculate the ratio of the length of P with that of Q. So I'm going to put 1 here, divide this by 2, divide this by 2. So I have that LP is equal to 1 over 2 LQ. All right? Let me finish it up here. Now, remember, LP is equal to 1 over 2 LQ. I have to divide both sides by LQ, divide LQ. They will cancel. We say that LP over LQ is equal to 1 over 2, which is something as 1:2. And that is the ratio of the original length of P to that of Q. Now, like I said earlier, we talked about the safety gap, which was part of the calculations given to us. Now, the issue is this. These are exactly one of the applications of expansion of heat or linear expansion to real world. The idea is simple. Based on what you're watching there, it says that on a sunny day, that the metal of the bridge extends more than normal. So if the engineer or the people who are building or the construction company refuse to give that gap between the bridge, what will happen is during this expansion, it will break the bridge, and then we say that the bridge has collapsed. One of the reasons for collapsing of building and collapsing of bridges and so many other things are the known technicality of some of the engineers, though not all of them. So welcome to this part, which is application of thermal expansion. What you are watching on the screen, which I have really shed a little light, can also be further application of thermal expansion include the expansion of buildings and steels, yes, which is it normal. Then railway lines, it is also applied, those gaps on the railway lines. The bimetallic stripe and its application, the wheel of the balance wheel of a clock and watches, then the thermostat, the control of the heat energy in your electric iron and all stuff. All these areas are where the expansion of or heat expansion are applied to real life situation. Thank you for being part of this class, but remember you have to hang around. We are going to solve a few more problems from Examguide app. Let's get started. Okay, we have the exam guide up here. There is a question here. Let's see. It said that the ratio of the coefficient of linear expansion of 2 meters, alpha 1, alpha 2, is 3:4. If, when heated through the same temperature change, the ratio of the length increase in length of the 2 meters is L1, E2 is 1/2. The ratio of the original length, L1, L2 is this. All right? We are going to play with this. So there is nothing special about this. Just like one of the ones we solved, we are going to follow the step one by one. Now, the ratio of the coefficient of linear expansion of 2 meters. So we have 2 meters, just like the last we solved. So alpha 1 and alpha 2. So let's say M1, M2. That is the first meter and the second meter. So what I'm going to do is alpha 1 is equal to L1 all over L times, okay, that's going to be L1. So let me call this change in L of the first one, then times change in temperature of the first one, yes? So the second one, I'm going to have the coefficient of expansion of the second meter is going to be change in length of the second one all over the length of the second one times change in temperature of the second one. That is what I have. Now, and they say that the ratio of these 2 meters linear expansivity is given as 3:4. So this divided by this is going to be 3/4. So now let me show you what. Alpha 1 all over alpha 2 is 3:4. That means this is the alpha 1 and this is the alpha 2. So I'm going to have L1 all over L1 times change in temperature 1 divided by L2 all over L2 times change in temperature 2 is going to be 3/4, because that's the question. That's what the question says. Now let's take the next step. If the heated, it said if when heated through the same temperature change, all right, the temperature change of this one must be the same temperature change of this. Therefore, I am going to negotiate with this one to call it 1 because they must be the same. That's what they're saying. That's the next statement. Now, the ratio of the increase in length of the 2 meters, E1 and E2 is 1/2. Okay, let's first of all clear this before we make subject formula of the increment in length, which is change in L1 and change in L2. So let's finish with this. So remember in mathematics, when there is division, the numerator goes up, the numerator comes down. So I have change in L1 all over L1 times change in theta 1 is going to be times, this is changing to times, so L2 times change in temperature of the first one all over change in length for the second one. Now, this will cancel this, all right? So I have that, and this is going to be equal to 3/4. So everything now have change in L1 all over L1 times L2 all over change in L2 is going to be 3/4. Now, I think there is a little violation of parameters. The first, what they gave me is E1 as the increment in length of the first one and increment in length of the second one. So what I'm going to do now is, I will say change in L1 is going to be E1 and change in L2 is going to be E2. So I will just change them now. In this case, I'm going to call this one E1 and I will call this one E2. Now, according to what they say, and they say that the ratio of the increment in length of the 2 meters, E1 stroke E2 is 1/2. Now, what I will do is E1 L2 all over E2 L1 is equal to 3/4. Let's finish it up there. So E1 over E2 times L2 over L1 is equal to 3 over 4. This is fun. So E1 over E2, E1 over E2 is 1 over 2. So everything here is going to be 1 over 2. I'm having 1 over 2 times L2 over L1 is equal to 3 over 4. So I'm going to transfer everything here to this part because I'm looking for L1 over L2, all right? So I'm going to multiply this one by 2 and then multiply this side by 2. So these two, we cancel these two. I have L2 over L1 is equal to 6 over 4. Now remember what I'm looking for is L1 over L2. So L1 over L2 is going to be 4 over 6, and which is 2 over 3. Do we have it there? 2 over 3, option A is the option. Thank you for participating in today's class. You can practice more questions using the Examguide app. The app scores and gives a detailed explanation of all the questions at the end of your practice test. You can learn a particular topic of interest with different modes like study mode, mock mode, and practice mode. It also has other features that makes learning fun. It is a must-have for all serious students. Download from www.examguide.com if you don't have it yet. See you in the next class. Don't forget to subscribe to our channel, hit the notification bell, and share the video to people that will benefit from it. Bye.